Tonight, from the Cosmic Lullaby channel, we present a special report that cuts through the noise of daily headlines to the very heart of global power, conflict, and survival. We are not looking at the actions of governments or the fluctuations of markets, but at a force more ancient, more powerful, and increasingly more volatile. We are turning our analytical gaze to the ever-raging world of weather. In an era defined by geopolitical friction and economic uncertainty, the most profound strategic shifts are not being orchestrated in war rooms or boardrooms, but in the endless dance of sky and storm that surrounds us every single day. The sky above our heads, so often taken for granted, may appear simple, a canvas for the sun and moon. But this is a dangerous misconception. In reality, it is a theater of unimaginable chaos and wonder, a volatile frontier that is becoming the new battleground for national security and economic dominance. Consider the atmosphere not as empty space, but as a living ocean of air, a turbulent, three-dimensional territory rippling with continent-spanning winds, painted with clouds of immense mass, and stirred by invisible rivers of heat that dictate everything from crop yields in the American Midwest to energy prices in Europe. In this fragile, interconnected system, a slight temperature anomaly in the Pacific can trigger catastrophic droughts in Africa and devastating floods in Southeast Asia, creating refugee crises and destabilizing entire regions. Within this system, sunlight, the source of all life, scatters into colors that have inspired artists for millennia. But it is also the fuel for storms born with the energy to cross entire oceans, storms that can cripple global supply chains in a matter of hours. Lightning, a force of raw, untamable energy, splits the sky with fire, reminding us of nature's untamed power. Weather is not merely the mood of the planet, it is its breath, its heartbeat, its song, a song that is growing louder, more dissonant, and infinitely more dangerous. The ability to predict, adapt to, and even influence these atmospheric forces is rapidly becoming the single most critical strategic variable in the 21st century. Let's begin with a fact that seems simple but holds the key to understanding the scale of power we are dealing with. A single, ordinary storm cloud can weigh more than 1,000,000 elephants. When you look up at a drifting cumulus cloud on a summer afternoon, it appears soft, ethereal, and weightless, like cotton pulled delicately across the sky. But this serene image masks an astonishing truth. That typical cloud, seemingly harmless, holds hundreds of thousands of tons of water, an unimaginable mass suspended miles above our cities and infrastructure. All those individual droplets, too small to be seen by the naked eye, add up to a weight heavier than 1,000,000 elephants standing side by side. Yet, against all logic, it floats. It is suspended in a delicate equilibrium because the water is dispersed into countless microscopic drops, each one carried relentlessly upward by rising columns of warm air. This is one of the great paradoxes of weather. The sight of something so immensely heavy, a potential deluge capable of causing billions in damages, appearing so delicate and ethereal. The next time you tilt your head to watch a cloud drift lazily overhead, remember that you are witnessing a force of nature in waiting. The overall mood of lakes, in its gentle embrace, a reminder of the colossal energies that are constantly in play above us, energies that can be unleashed with devastating consequences. This is not just a scientific curiosity, it is a matter of national security. The water held in these atmospheric reservoirs is a critical resource, and its distribution, where it falls and where it doesn't, is a primary driver of geopolitical stability. Now consider the energy within that cloud. Lightning is hotter than the surface of the sun. In the blink of an eye, a jagged bolt of lightning doesn't just split the sky. It unleashes a concentration of energy that defies comprehension. While it may look like pure white fire, its true temperature is even more startling, a data point that underscores the sheer violence of atmospheric physics. A single lightning strike can reach over 30,000 degrees Celsius, making it several times hotter than the surface of the sun itself. The energy involved is staggering, powerful enough to instantaneously superheat the air around it, transforming it into plasma and igniting the sky with a brilliance that can be seen from space. That sudden, violent expansion of superheated air is what we hear as thunder, a shock wave rolling across the landscape. Each flash of lightning is nature's own high-energy experiment, compressing unimaginable heat into a fraction of a second. Some of these bolts travel for miles, connecting the sky and the ground in a shimmering, destructive chain. For all its raw violence, lightning also plays a life-giving role, a duality that defines so much of our weather. It helps fix nitrogen into the soil, a natural fertilizer for the very plants that form the foundation of our global food supply. This single phenomenon is thus both a threat, capable of igniting wildfires that cost billions and disrupting power grids, and a necessity for the agricultural sector that underpins our economies. Understanding this duality is crucial to understanding the complex, often contradictory role that weather plays in our world. It is a force of creation and destruction, often in the very same instant. The sound we call thunder is the atmosphere audibly tearing itself apart. It is the sonic footprint of the immense energy release we have just witnessed. When thunder rolls low and deep across the sky, it can sound like distant drums of war, or, when close, a sharp and startling explosion. But what we are really hearing is the voice of lightning, a voice of pure, unadulterated power. When a bolt of lightning flashes, it heats the column of air it passes through so quickly and so intensely that the molecules expand in a violent, explosive rush, creating a shock wave that races outward faster than the speed of sound. That shock wave is thunder. The texture of the sound, a sharp crack versus a low rumble, is a direct function of your proximity to this atmospheric detonation. Light travels nearly 1,000,000 times faster than sound, which is why we see the flash long before the noise reaches our ears. This simple physical fact has been a fundamental strategic tool for centuries, allowing anyone to calculate the distance of an approaching storm. Counting the seconds between the flash and the sound provides a rough but critical estimate of how far away the danger lies. In this way, thunder is both a warning and a wonder, an auditory confirmation of the immense forces at play above us, a force that modern military and civilian infrastructure must constantly monitor. A single severe thunderstorm can disrupt flight patterns across an entire continent, costing the airline industry millions in delays and rerouting. The ability to track its movement down to the second is not a trivial matter. It is a critical component of logistical and economic stability. Now let us turn to the physical manifestation of the storm, the rain itself. Our cultural understanding of rain is often deeply flawed, shaped by simplistic imagery. Children's drawings and popular media have for generations shown raindrops falling as perfect teardrops, pointed at the top and rounded at the bottom. But the geopolitical and economic reality of water, the most critical resource on the planet, is as complex and misshapen as the raindrops themselves. In truth, they are nothing like teardrops. The smallest droplets are held in a near-perfect spherical shape by the force of surface tension, a testament to the fundamental laws of physics. However, as they grow larger and fall faster, the battle against air resistance begins. This atmospheric friction flattens their bottoms, contorting them into a shape more akin to a hamburger bun than a teardrop. If they grow too large, the aerodynamic stress becomes too great, and they can no longer hold their shape, breaking apart into smaller droplets in a violent mid-air collision.
This subtle detail is more than a scientific curiosity. It is a metaphor for the unseen pressures that shape our world. The illusion of the teardrop comes from how we observe water on a surface, stretched by gravity as it slides down a window pane. But the actual raindrops tumbling from the sky, destined to replenish the rivers that define our borders and water the crops that feed our nations, carry their own hidden geometry, tiny rounded jewels forged in chaos.
The arrival of this life-giving resource is announced by one of the most powerful and evocative scents in the natural world. There is a specific word for the earthy, profound fragrance that rises after a rainstorm: petrichor. This is not simply the smell of wetness. It is the scent of a complex chemical and biological event, a blend of remarkable ingredients that tell a story as old as the earth itself. During long dry spells, certain plants release aromatic oils that are absorbed into dry soil and rock. These oils are a survival mechanism, inhibiting seed germination to ensure plants do not sprout in conditions where they cannot survive. When raindrops finally strike the ground, they act as an aerosolizing agent. They trap tiny air bubbles in the soil that then shoot upward, carrying these ancient oils into the air for us to breathe. Simultaneously, a compound called geosmin, produced by soil-dwelling microbes, is released, filling the air with its rich, distinctly earthy perfume. This is the smell of life, of the very foundation of the terrestrial food chain. And there is a third, more violent component. During the storm, the same lightning that superheats the air also splits molecules of oxygen and nitrogen, creating ozone, which adds a sharp, clean, almost electric note to the mix. The result is the unmistakable smell of rain, a scent tied to ancient soils, living bacteria, and the raw chemical power of the sky itself. When you inhale that fragrance, you are breathing in a complex report on the state of the local ecosystem, a story of biology, geology, and atmospheric physics delivered directly to your senses. It is the perfume of a planet renewing itself, a process upon which our entire global civilization depends. When precipitation falls below the freezing point, it crystallizes into a form that has been romanticized for centuries, yet holds the power to paralyze entire nations: snow. We often picture snow drifting down in a silent, gentle ballet, each unique flake twirling in slow motion. While some snowflakes do indeed float gently, this idyllic image belies a far more chaotic and unpredictable reality. The speed of their descent is a complex variable, dictated by their size, mass, and aerodynamic structure. Small, delicate ice crystals may descend at just a fraction of a meter per second, hovering in the air as if reluctant to land. But larger flakes, aggregates of many crystals fused together, can tumble down at speeds closer to a few meters per second, accumulating with alarming speed. This is not a gentle ballet. It is a complex aerodynamic equation played out by trillions of individual particles. Wind currents further complicate this equation, transforming a vertical descent into a chaotic multi-directional assault, tossing flakes sideways, upward, and in disorienting spirals. In some cases, these frozen particles are carried for miles, becoming instruments in a vast atmospheric redistribution of water resources. When you witness snow falling, you are watching a process choreographed by air resistance, gravity, and the hidden architecture of ice, a process that determines the fate of winter crops, replenishes the reservoirs that supply our cities, and dictates the operational readiness of military forces in cold weather climates. The scale of what the atmosphere can produce in this frozen state is rarely appreciated. Most snowflakes we encounter are small, delicate crystals, no bigger than a fingernail. But under the right conditions, a precise combination of moisture, gentle winds, and specific temperatures, they can grow to extraordinary sizes. Flakes can stick together in mid-air,
forming massive clusters wider than a coin, or, in rare, documented cases, as large as a dinner plate. The largest snowflakes ever officially recorded, reported in Montana in the late 1800s, were said to be more than 15 inches across, larger than a hubcap. Imagine such immense, icy structures tumbling slowly from the sky, not as delicate flakes, but as tangible threats. While most of us will only ever see flakes the size of coins or smaller, knowing that the sky is capable of producing such giants adds a critical perspective to our understanding of weather. These are not just curiosities, they are data points that hint at the upper limits of precipitation events, extreme black swan possibilities for which our modern infrastructure is entirely unprepared. Each flake, regardless of its size, carries within it the complex geometry of ice crystals grown in the silent, frigid heights of the atmosphere, a microscopic blueprint for the massive winter storms that can bring a modern economy to its knees. When these elements combine with another atmospheric weapon, wind, the result is one of nature's most feared phenomena. A blizzard is not just a heavy snowfall, it is a full-scale assault where wind and snow merge into a blinding, suffocating wall of white. In the midst of a severe blizzard, visibility can drop to zero. Travelers and even emergency personnel caught in such conditions describe being unable to see their own hands held out in front of them, a state of total sensory deprivation. The snow is whipped into the air by powerful, unrelenting gusts, creating a swirling whiteout where all sense of direction vanishes, rendering GPS and other navigation tools useless at a human scale.
The overall mood is relaxed, engaging, and comfortable, perfect for bedtime reading and space narration. The temperature should be around 0 .9. In this environment, temperatures plummet, but the true danger is the wind chill, a measure of how quickly heat is stripped from the human body. It can freeze exposed skin in mere minutes. For nations in northern latitudes, blizzards are not inconvenient weather events. They are recurring national security threats. They have halted armies, crippled economies, and tested the resilience of power grids and emergency services to their absolute limit. To those living on open plains or in high mountains, blizzards are among the most dangerous of all weather events, capable of disorienting even the most experienced explorers and survival experts. And yet, within the storm's unrelenting ferocity, there is a strange, deceptive beauty. The transformation of the known world into a blank, featureless canvas of white, a place where an unnerving silence and a deafening chaos exist at the very same time. While blizzards represent a slow, suffocating threat, the thunderstorm possesses another weapon, one of direct, kinetic violence. It can turn frozen water into a form of atmospheric artillery, capable of inflicting billions of dollars in damage in a matter of minutes. This weapon is hail. When a thunderstorm's updraft is strong enough, raindrops are not allowed to fall. They are violently carried high into the freezing layers of the cloud, flash freezing into tiny pellets of ice. What follows is not a gentle descent, but a brutal cyclical journey. These ice pellets fall, gather more supercooled water, and are then seized by another violent updraft, hurled back up into the sub-zero altitudes to freeze a new layer of ice. This process can repeat dozens of times, and the result is a hailstone that has grown in perfect concentric layers, much like the layers of an onion or the growth rings of a tree. If you were to slice one open, you would be looking at a detailed record of its violent history, each layer a testament to a journey through the storm's turbulent heart. This is not a mere curiosity of meteorology. It is the production line for an incredibly destructive projectile.
Small hailstones may be harmless, but as they grow, their potential for destruction increases exponentially. Larger stones can shatter windows, perforate steel roofs, flatten entire fields of high-value crops, and inflict catastrophic damage on critical infrastructure like solar farms. The economic implications are staggering. A single 10-minute hailstorm over an agricultural region can wipe out an entire season's harvest, impacting commodity prices and futures markets globally. The global insurance industry pays out billions of dollars annually to cover hail damage to homes, vehicles, and businesses. In fact, hail is often the single most costly insured peril for property damage in many parts of the world. The largest hailstones can weigh more than a pound, striking the earth with the force of a blunt object dropped from a skyscraper. They are natural sculptures, yes, but they are carved by the turbulent breath of clouds and carry the memory of the storm in their icy, destructive design. The upper limits of this atmospheric weapon system are terrifying. In July of 2010, in the small town of Vivian, South Dakota, a supercell thunderstorm produced an astonishing piece of hail that fell from the sky. It was nearly the size of a volleyball, measuring 8 inches across and weighing almost 2 pounds. Imagine such a sphere of solid ice, a cryometeorite forged in our own atmosphere, hurtling toward the ground at speeds that can exceed 100 miles per hour. Fortunately, this record-breaking piece of natural artillery landed in a field rather than striking a person or a home, but it remains the largest hailstone ever officially measured in the United States. Around the world, other powerful storms have produced similarly enormous hailstones, each one formed by incredibly powerful updrafts that function like anti-gravity elevators, carrying them up and down inside storm clouds for extended periods, layering ice upon ice with each cycle. While most hailstones are no larger than peas, records like the one from Vivian serve as a stark reminder of nature's terrifying extremes. The sky, under these rare but increasingly frequent conditions, can produce ice missiles of a terrifying size and velocity, forged by turbulence and then hurled back down to Earth with immense destructive force. This is not just weather, it is a kinetic bombardment, and our modern sprawling cities and agricultural heartlands present an ever larger target for its fury. From the brute force of kinetic bombardment, we now turn to another of the supercell's weapons, one that concentrates atmospheric energy into a focused, spinning vortex of almost unimaginable violence. Tornadoes are among nature's most astonishing and terrifying forces, twisting across the land with winds so powerful they can turn the mundane into the unthinkable. One of the strangest and most unsettling pieces of tornado lore is, in fact, a documented reality. A fragile, lightweight piece of straw, when caught in the grip of a tornado, can be driven straight through a solid piece of wood. This is not a trick, it is a brutal lesson in physics. The winds accelerate debris to such extraordinary speeds that even the most harmless objects are transformed into piercing projectiles.
A natural male narrator voice with a warm, friendly tone. Fluid and easy to follow, like a light science podcast. Keep your voice clear and coherent, with a gentle intonation that is both intelligent and soothing. Use pauses when necessary. The overall mood should be relaxed, engaging, and comfortable, perfect for bedtime reading and space narration. The tempo should be around 0.90. After a powerful tornado has passed, forensic analysis of the damage reveals pieces of straw embedded deep in fence posts, utility poles, and even the walls of houses. This phenomenon serves as a chilling reminder of just how violent the air can become when it is spun into a vortex. A tornado doesn't need to carry heavy weapons. It weaponizes the immediate environment,
turning grass into arrows and styrofoam into shrapnel. To stand in the path of such a storm would be to face a force that fundamentally bends the rules of everyday reality, where fragile, insignificant things become deadly instruments of destruction. This capability has profound implications for infrastructure and building codes. Standard construction is designed to withstand linear wind forces, not high-speed projectile impacts from every conceivable angle. A tornado's destructive power comes not just from its wind speed, but from the debris it hurls, effectively sandblasting buildings and infrastructure into ruin. The sheer velocity of these winds places tornadoes in a class of their own. When we think of powerful winds, we may picture hurricanes battering a coastline. But in terms of concentrated wind speed, tornadoes leave even the most powerful hurricanes in the dust. The most intense tornadoes, classified as EF5s on the enhanced Fujita scale, have had their wind speeds measured at more than 300 miles per hour. This is a velocity comparable to the cruising speed of a passenger jet. In such winds, the laws of physics seem to break down. Heavy freight cars can be lifted and tossed into the air like toys. Massive steel-reinforced beams can be bent and twisted into unrecognizable shapes. And entire buildings can be scoured from their foundations, leaving nothing but a concrete slab. The economic devastation is absolute.
A natural male narrator with a warm, friendly tone. The overall mood should be relaxed, engaging, and comfortable, perfect for bedtime reading and space narration. The tornado is a scalpel of atmospheric fury. The hurricane is a sledgehammer, a storm on a scale that almost defies comprehension. Spanning hundreds of miles and fueled by the immense thermal energy of warm ocean waters, a hurricane gathers moisture and heat, building itself into a vast, spinning planetary engine. To truly grasp the power we are dealing with, consider this single staggering fact. The energy released in a single day by a mature hurricane is greater than the combined energy output of every power plant on Earth. Let that sink in. Imagine every coal plant, every nuclear reactor, every wind turbine, and every solar panel in the world feeding their power into one grid for 24 hours. The total output would still fall short of the energy unleashed by a single storm. This is not a metaphor. It is a calculated reality. The overall mood of this colossal energy is released as heat, carried away by the condensation of billions of tons of water vapor, while the rest is unleashed as the storm's kinetic output, the fierce, destructive winds, and the pounding, coastline reshaping waves. The economic and geopolitical implications of this energy release are profound. A single major hurricane can disrupt global energy markets by shutting down oil and gas production in critical areas like the Gulf of Mexico. It can sever global supply chains by closing major shipping ports for weeks. It can inflict damage costing tens or even hundreds of billions of dollars, erasing a nation's annual GDP growth in a matter of days. To stand at the edge of a hurricane is to feel just the faintest brush of its power, while only satellites orbiting in space can capture its swirling, terrifying immensity. It is Earth's most spectacular and most expensive weather machine. Yet, within this sprawling vortex of violence lies one of the most bizarre and deceptive paradoxes in all of meteorology. The calmest part of a hurricane is found at its violent center. To step into the eye of a hurricane is to experience something almost unbelievable, a phenomenon that has baffled and terrified sailors for centuries. After enduring hours of howling, apocalyptic winds and torrential horizontal rain, a sudden, shocking silence falls. The air clears, the punishing clouds part, and sometimes the sun or stars will even shine down into the abyss. This is the eye,
a roughly circular region at the very heart of the storm, often 20 to 40 miles wide. Here, the winds become eerily calm, and the sea surface, once a chaotic turmoil, can become strangely steady. But this is not a place of safety. It is a trap.
It is a brief, false peace in the middle of a war. Surrounding this tranquil eye is the eye wall, a towering circular ring of the most violent thunderstorms on the planet, where the storm's winds reach their absolute peak velocity and its destructive power is at its most concentrated. The eye is like the still, silent hub of a spinning wheel, calm only because the chaos rages so fiercely and so perfectly around it. For those who have experienced it and survived, on ships, in coastal towns, or as part of hurricane hunter flight crews, the eye is an unforgettable experience, simultaneously eerie, peaceful, beautiful, and filled with a profound sense of dread. This dread comes from the certain knowledge that the reprieve is temporary. After a brief, deceptive pause, the storm will return with the full, unrestrained force of the opposite eye wall. From the concentrated, mobile fury of the hurricane, we now broaden our analysis to a phenomenon of even greater scale, a seasonal, continental weather engine upon which the lives and livelihoods of nearly half the world's population depend. In many parts of the globe, life is tied not to the daily forecast, but to the epic annual rhythm of the monsoons. These are not mere seasonal winds, they are a complete reversal of the dominant atmospheric flow, a planetary scale shift that brings with it immense, life-giving, and often catastrophic rains. For months on end, vast landscapes may lie parched and cracked under a relentless sun, waiting for relief as temperatures soar and rivers run dry. Then, with a speed that can seem almost supernatural, the skies open. Rivers swell from trickles into raging torrents, fields are inundated, and entire continents come alive with an explosion of green. The monsoon is the ultimate double-edged sword. Its rains are both profoundly life-giving and terrifyingly destructive. They are the primary source of water for the crops that feed hundreds of millions of people, forming the very backbone of the economies of nations like India, Vietnam, and Indonesia. A successful monsoon can lead to a booming economy, reduced inflation, and social stability. A failed or late monsoon can trigger widespread crop failure, food shortages, and political unrest, creating shockwaves that are felt in global commodity markets. At the same time, these same life-giving rains can unleash biblical floods and catastrophic landslides that reshape the very land itself, displacing millions and costing billions in infrastructure damage. In India, Southeast Asia, and parts of Africa, entire cultures, histories, and socioeconomic structures have evolved in a delicate, often precarious harmony with the annual cycle of the monsoon. This is not an exaggeration. The timing and intensity of the monsoon are the most critical data points for these nations. Farmers plant and harvest according to its ancient timing. National budgets are planned around its predicted strength. Religious festivals, celebrated by hundreds of millions, mark its arrival with a mixture of hope and trepidation. The monsoon is the hydro-political fulcrum of the region. To witness its arrival is to see weather on a continental scale, a turning of the entire atmosphere so vast and so powerful that it changes the face of nations and holds the fate of a significant portion of humanity in its watery embrace. The stability of this entire region, home to multiple nuclear powers and a third of the world's population, rests on the predictable performance of this single, massive weather phenomenon. Its increasing volatility and a changing climate is therefore one of the most significant geopolitical threats of the 21st century. From the superabundance of water that defines the monsoon, we now pivot to its absolute and terrifying absence.
There are dry places on Earth, and then there is the Atacama. Stretching across the high plateaus of northern Chile, it is widely considered the driest non-polar desert on the planet. This is not a landscape that experiences occasional drought. It is a region in a state of perpetual extreme aridity. Some weather stations located in the heart of the Atacama have never recorded a single drop of rain in their entire history of operation. Parts of this desert may go decades, even centuries, without any measurable precipitation. This is an environment so hostile to life, so stripped of water, that its soil is considered a terrestrial analog for the surface of Mars. NASA and other space agencies actively study the Atacama to test rovers and life detection equipment, preparing for missions to the Red Planet. In a world where access to fresh water is becoming a primary driver of geopolitical conflict, the Atacama serves as a stark case study in resource scarcity. The silence of this place is the silence of a landscape almost untouched by conventional weather. And yet, even here, in this profoundly alien environment on our own planet, life finds a way to cling to existence. Certain specialized plants have evolved to draw all the water they need from the fog that occasionally drifts in from the Pacific coast, while resilient microorganisms lie dormant deep in the hyper-arid ground waiting for a miracle. On the rare occasions when that miracle does arrive and significant rain falls, the desert explodes into a riot of color. Dormant seeds spring to life, carpeting the barren sands in a breathtaking spectacle of wildflowers called the Desierto Florido, the flowering desert. This rare event underscores a critical point. The potential for life is locked away, waiting only for the one element that weather so rarely delivers here. To stand in the Atacama is to feel the profound weight of a sky that withholds, a place where every single drop of water is a strategic resource of unimaginable value. The mineral wealth beneath its soil, particularly lithium and copper, makes it a region of immense economic importance. Yet all operations are constrained by the absolute lack of its most vital resource, a constant humbling reminder of weather's ultimate authority. From the absolute silence of a sky that withholds, we travel to the other side of the planet and to the opposite extreme of the hydrological spectrum. Here, the sky does not withhold. It gives until there is nothing left to give, creating the wettest inhabited place on the face of the earth. In the northeastern hills of India lies the village of Masinram. This small community holds the global record for average annual rainfall, a figure so immense it is difficult to comprehend. Each year, the monsoon winds, saturated with moisture from the vast Bay of Bengal, are funneled directly into the surrounding Khasi Hills. This unique geography forces the moist air rapidly upward in a process known as orographic lift, squeezing the water from the atmosphere with unparalleled efficiency. The result is an average annual rainfall of nearly 12 meters, or just under 40 feet. To put that into perspective, this single village receives more rain in an average year than many of the world's major cities, like London or Seattle, receive in a decade. The overall mood of deluge, where rivers literally roar down the streaks, where new waterfalls surge from cliffsides daily, and where the sound of falling water is a constant, unending companion to every moment of life. This is not an environment that humans can simply inhabit. It is one they must constantly fight against and adapt to in extraordinary ways. Standard construction materials fail rapidly. Roofs must be built of sturdy, resilient materials simply to withstand the physical force of the deluge. The most stunning example of this adaptation is a form of living, bioengineered infrastructure. Instead of building bridges from steel that would rust or wood that would rot, the people of this region have learned to weave living bridges from the aerial roots of rubber fig trees. These structures are guided across swollen rivers and streams, and over decades they grow into immensely strong, living structures that are self-reinforcing and become more resilient the more rain they endure. This is a profound lesson in sustainable engineering, a stark contrast to modern infrastructure that is often brittle and fails in the face of extreme weather. Life here is not just shaped by rain, it is dictated by it, a continuous hydrological siege. While most of the world measures precipitation in inches or centimeters, in Masanram it is measured in towering, unimaginable walls of water that return every single year without fail. The village is a living laboratory, demonstrating the absolute limits of human resilience and serving as a powerful reminder that weather is not evenly spread across the globe.
The overall mood of a place like Mas and Ram, which must constantly manage a catastrophic surplus of water, and the Atacama, which suffers from its absolute absence, defines the fundamental hydropolitical imbalance of our planet, an imbalance that is a growing source of instability and conflict. From the extremes of water, we now turn our focus to the extremes of its thermodynamic opposite, fire, in the form of pure ambient heat. In July of 1913, in a place appropriately named Death Valley, California, a superheated furnace-like wind swept across the barren desert floor. The official temperature that day, measured at a weather station, was 56.7 degrees Celsius, or 134 degrees Fahrenheit. This remains the hottest reliably recorded air temperature in human history. To comprehend such a temperature is to imagine an environment actively hostile to life and technology. At such heat, asphalt on roads softens into a viscous tar. Exposed metal can cause severe burns to the touch, and car tires risk melting or failing if driven for too long. The human body, a finely tuned biological machine, begins to lose its battle to shed warmth. Without a constant supply of water, survival becomes a matter of hours, even in the shade. Death Valley earned its name from precisely these extremes, where the daytime heat rises off the rocks in shimmering, disorienting waves. Though other locations, like Kuwait or Iran, have recorded temperatures that come close, Death Valley's official record still holds the crown. This is not merely a record in a book, it is a critical data point representing the upper threshold of what our planet's atmosphere can produce. Extreme heat is a silent, invisible killer and a massive economic inhibitor. Unlike a tornado or a flood, its damage is not immediately visible, but it is just as profound. Heat waves ground flights, warp railway lines, and push electrical grids to the point of catastrophic failure as demand for air conditioning skyrockets. They have a direct, measurable impact on labor productivity, particularly in agriculture and construction, costing the global economy hundreds of billions of dollars annually. The fact that such temperatures exist naturally on our own planet is a stark reminder of the atmosphere's power. The air above us is not always mild and gentle. Under the right conditions, it can become a blazing, deadly furnace, capable of bringing the complex machinery of modern society to a grinding halt. From the planet's blazing furnace, we now travel to its opposite pole of thermal extremity, the frozen heart of Antarctica. At a high, desolate plateau far from any sea lies the Russian research outpost Vostok Station, a place where the very air itself feels alien. Here, in the winter of 1983, scientists recorded the lowest natural temperature ever directly measured on Earth, a stunning minus 89.2 degrees Celsius. More recently, satellite thermal mapping has detected even lower surface readings in nearby hollows, approaching a staggering minus 98 degrees Celsius. To call this cold is an understatement. This is an absolute, fundamental cold, a temperature so low it operates at the boundary of physics and biology as we know them.
It is colder than dry ice, cold enough to make high-grade steel brittle and cause it to shatter like glass. In such conditions, a cup of boiling water thrown into the air will not fall as liquid. It will explode into a cloud of ice crystals. Human breath freezes instantly, falling to the ground as a shimmering dust. Any exposed skin will suffer severe frostbite in seconds. This environment is, on average, colder than the surface of Mars. To live and operate here requires extraordinary technological preparation, with heated, pressurized shelters, multi-layered insulated suits, and constant, unwavering vigilance. Yet Vostok Station is more than just a monument to human endurance. It is a critical geopolitical foothold on a continent governed by a fragile international treaty. Antarctica's strategic importance is immense, not only for its potential untapped resources, but for its central role in regulating the planet's climate. The scientific work done here is of paramount importance. By drilling deep into the ice sheet, scientists at Vostok have extracted ice cores containing air bubbles from 400,000 years ago, providing us with an unbroken record of Earth's past climate, the very data that underpins our entire understanding of atmospheric change. This is the ultimate frontier of cold, a cryogenic laboratory where the Earth's atmosphere meets its most extreme and profound silence, and in that silence reveals the deepest secrets of its own history. The spectacular violence of tornadoes and the brutal cold of the poles often dominate our perception of dangerous weather. Storms and floods make for dramatic headlines, their power visible and immediate. But the single deadliest form of weather is far quieter, more insidious, and far more widespread: the heat wave. When a stagnant dome of high pressure traps air over a region and temperatures soar for days or weeks on end, the human body begins a desperate losing battle. Without relief, particularly during the night, heat stress builds relentlessly, straining cardiovascular systems and leading to dehydration and organ failure. This is a threat that is amplified by our own modern environment. Cities, with their vast expanses of asphalt, concrete, and steel, absorb and retain solar radiation far more effectively than natural landscapes. The overall mood of heat waves creates what is known as the urban heat island effect, where metropolitan areas can be several degrees warmer than the surrounding countryside. At night, this stored heat is slowly released, preventing the natural cooling that is essential for human recovery. The city itself becomes a thermal trap. Around the world, heat waves have claimed tens of thousands of lives in recent decades, often silently. They disproportionately affect the most vulnerable: the elderly, the very young, and those without access to shelter or air conditioning. Unlike a storm, you cannot see its violence, but the evidence is there in the overwhelming of emergency services, in rising hospital admissions, and in the quiet, tragic increase in mortality rates. The impact extends beyond human health. Heat waves decimate agriculture, leading to withered crops in the fields and massive die-offs of livestock. They heat rivers and lakes to temperatures that can kill fish by the thousands, triggering ecological collapse. Heat waves are weather's most insidious threat, a slow, creeping siege that arrives not with a roar, but with a suffocating silence, inflicting devastating casualties with its oppressive, unrelenting power. As urban populations continue to grow, the amplification of this threat by our own infrastructure is a critical challenge for public health and city planning worldwide. From the oppressive clarity of a heat wave, we shift to a weather phenomenon that threatens not with energy or temperature, but with its complete and total absence: the absence of visibility. Fog is one of weather's quietest and most deceptive tricks. It is, in essence, a cloud that has formed at ground level, wrapping the world in a pale, disorienting silence. Typically, it makes the horizon vanish, blurring the familiar shapes of buildings and trees into ghostly apparitions. But in rare cases, fog can become so thick that visibility shrinks to just a few feet. People caught walking in such conditions describe the unnerving sensation of being unable to see their own feet clearly on the ground. In this kind of fog, the laws of acoustics also seem to change. Sound is muffled, distorted, and feels unnervingly close, as if the air itself has become a thick, absorbent blanket. While it may seem like a soft and harmless phenomenon, dense fog is one of the most dangerous and economically disruptive weather events. For modern high-speed transportation systems, it is a paralyzing agent. A single dense fog event can shut down major international airports for hours, grounding entire fleets of airplanes, creating a cascading effect of delays and cancellations that costs the global economy hundreds of millions of dollars. It can bring maritime shipping in critical channels to a crawl, and is a primary cause of catastrophic multi-vehicle pileups on major highways. Despite its softness, fog is a silent killer. And yet, to move through it is to experience something profoundly otherworldly, like walking inside a dream where the hard edges of reality have completely dissolved, leaving only an oppressive whiteness and the sound of your own muffled breath. It is a stark reminder that one of the most critical elements for the functioning of our advanced society is the simple ability to see. An ability that the atmosphere can revoke at a moment's notice, plunging our world into a state of blind, silent chaos. Even in environments where fog does not form and rain is a distant memory, the atmosphere can deliver water in a more subtle yet equally critical way. In the profound silence of the world's great deserts, dew is a quiet savior. As the sun sets, the ground, stripped of cloud cover, radiates its heat back into space and cools rapidly. If the air temperature dips below a certain point, the dew point, moisture in the air that was invisible gas by day, condenses directly onto surfaces. Each morning, the desert awakens adorned with countless tiny beads of water, on rocks, on the leaves of sparse plants, and even on individual grains of sand. For the specialized ecosystems that have evolved to survive in these punishingly arid regions, this daily deposit of dew can be the deciding factor between life and death. It is a resource harvested with ingenious efficiency. Certain species of beetles in the Namib Desert tilt their bodies into the wind, allowing droplets to collect on their shells and run down into their mouths. Plants have evolved to channel the dew down their stems directly toward their thirsty roots. This microscopic daily water source is what sustains life in a place where rain may not fall for months or even years. Humans have also learned to harvest it. In several arid regions, from the Atacama to the Canary Islands, large nets are constructed to passively collect this atmospheric moisture, providing a crucial source of potable water for isolated communities. Though each droplet is infinitesimally small, together they provide sustenance and represent a strategic resource in places of extreme scarcity. Dew is, in effect, desert rain, delivered not in a storm, but in a whisper. When temperatures drop below freezing, this same process of condensation creates a different phenomenon. Frost crystals can grow into intricate, spiky forests of ice. On frigid winter mornings, frost often paints delicate fern-like patterns on window panes or leaves. A natural male narrator forming as water vapor bypasses the liquid state and freezes directly onto a cold surface. But in the right conditions of extreme cold and still, humid air, frost can grow into something far larger and stranger. On mountain peaks and across polar plateaus, it can form into spiky forests of ice known as hoarfrost. Here, the crystals grow outward into jagged, interlocking towers, sometimes inches long, that catch the morning light like sculptures of spun glass. This is more than just a beautiful occurrence. For agriculture, a sudden, unexpected frost can be an economic disaster, flash freezing and destroying sensitive crops and costing farmers millions of dollars in a single night. This fragile crystalline forest, born from nothing more than cold air and water vapor, is another example of weather's power to create beauty and inflict destruction at the most delicate of scales. There is a form of winter storm that combines the destructive potential of a blizzard with the insidious danger of fog. A storm that does not blow cities apart but paralyzes them, encasing them in a beautiful but catastrophically heavy shell of glass. There is a profound beauty in an ice storm, but it is the kind of beauty that is edged with extreme danger. This phenomenon occurs under a specific and treacherous set of atmospheric conditions. When rain falls from a milder layer of air high above, it must then pass through a shallow layer of sub-freezing air close to the ground. The drops do not have time to freeze into sleet. Instead, they become supercooled liquid. They remain purely liquid as they fall, yet they are poised to freeze the instant they touch any surface. The result is a landscape transformed. Roads and sidewalks glaze over into perfect, invisible sheets of ice, making travel impossible. Tree branches, power lines, and every exposed surface are coated in layer after layer of clear, heavy ice, turning the world into a forest of crystal sculptures. At night, the light from street lamps and headlights refracts through this icy casing, creating a world of shimmering, breathtaking reflections. But beneath this spectacular brilliance lies a direct and devastating assault on the most critical infrastructure of modern society, the electrical grid. Power lines, designed to carry electricity, are not designed to support tons of accumulating ice. A single half-inch of ice can add hundreds of pounds of weight to a span of electrical wire. As the ice storm continues, this weight becomes immense, causing lines to sag, stretch, and eventually snap. The true danger, however, comes from the trees. Encased in thousands of pounds of ice, massive branches and entire trees crack under the strain and fall, crashing down onto the power lines below. The result is a cascading failure of the grid. Entire neighborhoods, cities, and even regions can lose power for days, or, in severe cases, for weeks. This is weather at its most deceptive. It arrives not with a roar, but with a quiet, persistent ticking sound as the freezing rain accumulates. The danger is not in the wind, but in the simple, relentless force of gravity acting on the ever-increasing weight of the ice. To be in a severe ice storm is to move through a fragile, glittering world of frozen jewels, where every surface is treacherous and the eerie sound of snapping tree limbs is a prelude to the profound silence of a city plunged into cold and darkness. From the paralyzing cold of an ice storm, we return to the world of intense, dry heat, where the atmosphere displays its power not with precipitation, but with pure kinetic energy. On a hot, still, arid afternoon, the ground can heat unevenly, creating pockets of superheated air that begin to rise. Sometimes this rising column of air will begin to spin, picking up dust and debris and forming a vortex known as a dust devil. Many of these are small, harmless whirlwinds, just a few feet across. But some can grow to astonishing and dangerous proportions, becoming twisting towers of dust and sand that rise taller than modern skyscrapers. Unlike tornadoes, which are born from the violent rotation within a supercell thunderstorm, dust devils form under clear, sunny skies, seemingly out of nowhere. They dance across deserts, agricultural fields, and even paved parking lots, driven by the intense thermal energy radiating from the ground. While the smaller ones are merely a nuisance, the largest can be a significant threat. A powerful dust devil can topple fences, tear sheet metal from roofs, and hurl debris across the ground with considerable force. Pilots flying over desert regions have reported seeing these massive dust devils from the air, towering over the landscape like temporary, chaotic giants, posing a serious and unpredictable hazard to low-flying aircraft, particularly helicopters and drones. This phenomenon is not just a terrestrial curiosity. It has interplanetary significance. Dust devils are one of the most prominent weather features on the surface of Mars. The Martian rovers have imaged hundreds of these vortices, some many times larger than their terrestrial counterparts. Studying how dust devils form and behave on Earth provides critical data for understanding the Martian atmosphere, how dust is transported across its surface, and the challenges future human missions will face. They are, in a very real sense, a direct atmospheric analog for a key weather process on another world. To watch one form is to see the invisible currents of heat and air made suddenly and dramatically visible. A chaotic and mesmerizing whirlwind that reveals just how alive and how powerful the atmosphere is, even on days that appear perfectly calm. From the dry thermal vortices of the desert, we now turn our attention to their aquatic counterparts, a phenomenon that occurs when the same rotational energy forms over water. Imagine standing on a shoreline and witnessing a slender, twisting column of mist and spray rising from the sea, stretching up to connect with the dark base of a cloud above. This is a waterspout, a vortex of air and water that has the shape of a tornado but is born over the ocean. Meteorologically, they are divided into two types: tornadic waterspouts, which are true tornadoes that form over water, and the more common fair weather waterspouts, which form in a similar manner to dust devils, driven by rising air and temperature differentials. Some of these are relatively weak, spinning harmlessly across bays or lakes before quickly dissipating. Others, however, are powerful enough to pose a significant and direct threat to maritime activities. A strong waterspout can easily capsize small boats, snap the masts of larger vessels, and whip the sea into a localized frenzy. For centuries, fishermen and sailors have told stories of these ghostly funnels looming on the horizon, treating them with a mixture of awe and fear. From a distance, they can be strangely and hauntingly beautiful, appearing as spirals of silver mist gliding silently across the surface of the sea, illuminated by sunlight, or, more ominously, by lightning from the storm cloud that spawned them. But up close, they are revealed to be forces of pure chaos, a violent blending of storm winds and ocean spray. In the modern era, waterspouts are not just a threat to small vessels. They pose a serious risk to the multi-billion-dollar offshore energy industry. A direct hit on an oil rig or a wind turbine installation could cause significant damage. Furthermore, they are a major hazard in busy coastal shipping lanes and to port operations. Waterspouts serve as a crucial reminder that the atmosphere's rotational fury is not confined to land. Even the apparently calm open sea can, under the right conditions, suddenly twist itself into a whirling tower of water, reaching from the surface of the ocean to the base of the sky. From the visible rotation of the waterspout, we now examine a threat that is far more dangerous precisely because it is invisible. Microbursts are among the most lethal and least predictable threats in all of meteorology. They occur when a thunderstorm, instead of sustaining its updraft, suddenly dumps a concentrated mass of cold, dense air. This air plunges toward the ground like a stone and then spreads outward in all directions at incredibly high speeds upon impact. To an observer on the ground, a microburst might feel like a sudden, violent, and inexplicable blast of wind, powerful enough to knock down mature trees or flatten entire fields of crops in a straight line. But for aviation, the danger is catastrophic. A plane flying into a microburst faces a sequence of deadly aerodynamic traps.
First, it encounters a strong headwind, then a powerful downdraft, and finally a sudden disorienting tailwind. This sequence can cause a plane to lose all aerodynamic lift in a matter of seconds, forcing it downward faster than even the most skilled pilot can react. For decades, microbursts were a mystery, an unseen killer responsible for a number of tragic airline accidents where planes seemingly fell out of the sky on final approach. It was only through the forensic analysis of these disasters that their deadly potential was fully understood, leading directly to the development of new safety systems like terminal Doppler weather radar, specifically designed to detect them near airports. Microbursts are incredibly short-lived, sometimes lasting for only a few minutes, but their power is immense, with outflow winds that can exceed 100 miles per hour. They are a terrifying example of how a storm can unleash its fury, not just with lightning and rain, but with sudden, invisible, and catastrophic blasts of downward-moving air. They represent a hard-won lesson in our understanding of the atmosphere, a threat that was only identified and countered after it had already claimed hundreds of lives, proving that sometimes the most dangerous forces are the ones we cannot see. Microbursts, tornadoes, and giant hail are not random acts of atmospheric violence. They are often the specific products of a rare and highly organized type of storm, a true monster of the atmosphere. Most thunderstorms are relatively small, localized events, lasting less than an hour before dissipating. But supercells are different. They are massive, self-sustaining storm systems defined by a deep, persistently rotating updraft known as a mesocyclone. This rotation allows them to last for many hours, traveling across entire states as coherent engines of destruction. On satellite and radar imagery, a supercell can stretch for hundreds of miles, sometimes appearing larger than entire U.S. states. Within their towering cloud structures, which can rise more than 10 miles into the stratosphere, entire ecosystems of violent weather come to life simultaneously. A single supercell can produce lightning flashing thousands of times per minute, hailstones forming layer upon layer in its powerful updraft, and multiple long-lived tornadoes spinning into existence from its rotating base. Supercells are relatively rare, but they are the engines of the most destructive and costly weather on Earth, responsible for a disproportionate amount of damage from high winds, hail, and nearly all strong tornadoes. To watch one of these storms forming from a safe distance is to witness the atmosphere flexing its muscles on a terrifying scale. It often appears as a dark, rolling, striated wall of cloud so vast it reshakes the entire horizon, a structure that seems almost alive. The persistent rotation gives it a distinct, organized, and menacing appearance, fundamentally different from a common thunderstorm. They are storms that seem to breathe and grow, dominating the landscape to such a degree that the ground beneath them feels insignificant. The overall mood of the supercell is one of the highest priorities in meteorology, as the ability to predict their formation and track their movement is a matter of life and death for those who lie in their path. While the supercell represents the peak of a thunderstorm's organized intensity, there are other structures that are remarkable for their sheer endurance. We often think of thunderstorms as fleeting events, a quick, violent burst of lightning followed by clearing skies. But under the right atmospheric conditions, thunderstorm systems can persist for far longer, becoming a threat not because of their peak intensity, but because of their unrelenting duration.
Systems known as mesoscale convective complexes, or MCCs, can last for 12 hours or more, traveling for hundreds of miles across entire regions while maintaining their intensity. These are not single storms, but sprawling, organized masses of multiple thunderstorms that function as a single self-sustaining entity. Within them, new storm cells constantly rise and collapse in a regenerative cycle, feeding on the warm, moist air of the nighttime low-level jet stream. This nocturnal nature makes them particularly dangerous, as they often reach peak intensity while people are asleep. From satellite imagery, they appear as massive, roughly circular canopies of cloud, often glowing with nearly continuous flickering lightning. While they lack the violent rotation of a supercell, these long-lived thunderstorms can cause widespread and catastrophic flooding by releasing torrents of rain over the same area for many hours. For agricultural regions like the American Midwest, they are a critical source of overnight rainfall during the growing season, but they can also bring damaging straight-line winds and hail. For those living beneath one of these complexes, the storm becomes an oppressive, seemingly eternal companion through the entire night.
The overall mood of weather does not always operate on a brief, dramatic timescale. Sometimes the sky itself settles in for a long, restless, and dangerous stay. From storms that are remarkable for their duration over a single night, we now turn to a weather phenomenon that is astonishing for its persistence over centuries. At the mouth of the Catatumbo River in Venezuela, where it empties into Lake Maracaibo, a storm has been raging in the same spot for as long as recorded history. Known as the Catatumbo lightning, this is a unique and powerful natural phenomenon where thunderstorms occur almost nightly, sometimes for 10 hours at a time, for more than 200 nights each year. The relentless semi-permanent nature of this storm is the result of a perfect and unique convergence of local geography and meteorology. Warm, moist winds blowing from the Caribbean Sea are funneled into the Maracaibo Basin, where they are then forced upward by the cold, dense air descending from the high peaks of the Andes Mountains that surround the lake on 3 sides. This reliable, daily atmospheric collision creates the perfect recipe for constant, intense, and localized storm generation. From miles away, the sky above the lake glows with an almost continuous, silent flickering of intracloud lightning, a natural fireworks display so consistent that for centuries, sailors on the Caribbean Sea used its predictable glow as a navigational beacon. They called it the Lighthouse of Maracaibo. Scientists are still studying the precise dynamics that make this one location so uniquely prone to storm formation, but its significance is undisputed. The Catatumbo lightning is believed to be the world's largest single generator of tropospheric ozone, playing a key role in the chemistry of the upper atmosphere. It is a natural laboratory for studying the physics of lightning. Nowhere else on Earth does lightning pulse with such relentless, predictable, and timeless rhythm. A storm that is not just a passing event, but a permanent feature of the landscape itself. To understand and predict the complex phenomena we have discussed, from localized storms to continental weather systems, humanity has developed an array of sophisticated tools. Yet, the foundation of all modern weather forecasting begins with a remarkably simple and reliable piece of technology: the weather balloon. Every single day, at hundreds of locations around the globe, these large balloons filled with helium or hydrogen are released into the sky, carrying a small, instrument-packed payload called a radiosonde. These balloons ascend at a steady rate of about 1,000 feet per minute, drifting far above the altitude of commercial airliners and through the highest clouds, deep into the stratosphere itself.
By the time the atmospheric pressure causes them to burst, they may have reached an altitude of over 20 miles, soaring much higher than the peak of Mount Everest. At these extreme altitudes, the air is so thin and frigid that temperatures can plunge to -90 degrees Celsius, and the blackness of space becomes visible against the curve of the Earth's horizon. Throughout their entire ascent, these balloons are not passive observers. The radiosonde is constantly measuring the fundamental properties of the atmosphere at every level: temperature, air pressure, humidity, and wind speed and direction. It then transmits this invaluable data back to Earth in real time. This information is the bedrock of weather forecasting.
While satellites can see the tops of clouds, weather balloons provide a vertical profile of the atmosphere, a slice of ground truth that is absolutely essential for the complex computer models that predict the weather days in advance. Though they are unseen by most of us, these silent, high-altitude explorers are one of our most critical tools for mapping the invisible, ever-changing ocean of air that surrounds our planet. While weather balloons provide the critical vertical data from within the atmosphere, our ability to see the entire system from above has revolutionized forecasting. Orbiting hundreds of miles above the Earth, a fleet of sophisticated weather satellites watches over us like silent, all-seeing guardians. When a massive storm system like a hurricane begins to form over the vast, empty expanse of the ocean, these satellites are the first to see it, capturing its nascent spiral arms and its developing eye. From the cold, silent vantage point of space, a hurricane is a thing of breathtaking, terrifying beauty, a perfect swirling geometry of clouds in endless rotation. But within those graceful, mesmerizing patterns lies the mathematical certainty of devastating power. Modern satellites do more than just take pictures. They are multispectral imaging platforms, capable of tracking storms in real time across different wavelengths of light. They map rainfall intensity, use microwave sensors to measure wind speeds over the ocean, and peer inside the storm with infrared sensors to analyze the heat signatures of its cloud tops, a key indicator of its strength and development. This constant 24/7 vigilance is arguably the single greatest life-saving tool in the history of meteorology, giving coastal cities and nations precious hours or even days to prepare for landfall. Before the satellite era, powerful storms would often strike with little to no warning, leading to catastrophic loss of life.
But now, from the moment they are born over the sea, we can watch them grow, track their precise path, and eventually watch them fade back into the sea. From the cold silence of low Earth orbit, our satellites see Earth's most violent storms not as random chaos, but as massive, organized, and increasingly predictable living patterns. They have turned the entire planet into a knowable system, stripping the sky of some of its oldest and most deadly surprises. While satellites provide the indispensable top-down strategic view of the atmosphere, another technology allows us to peer inside the storms themselves, to dissect their internal anatomy in real time. When a storm approaches, the familiar green and red patterns we see on weather maps are made possible by radar. But modern Doppler radar does far more than simply detect the presence of rain. By bouncing radio waves off of raindrops, snowflakes, and even hailstones, it can precisely measure not only their location, but also their velocity and direction of movement relative to the radar dish. This is the famous Doppler effect, the same principle that makes a siren change pitch as it passes you. This single technological leap, the ability to see the motion within a storm, was a revolutionary advance in meteorology. It allows meteorologists to see inside a storm's heart with astonishing detail, tracking the telltale rotation that could spawn a tornado long before one actually touches down, or identifying the specific bands of heavy, stationary rain that could lead to a catastrophic flash flood. In effect, Doppler radar turns the invisible, chaotic movements of the atmosphere into a clear, visible map, a detailed portrait of swirling chaos translated into actionable intelligence. The overall move of national Doppler radar networks, like the NEXRAD system in the United States, was a massive public infrastructure project that has paid for itself many times over in lives and property saved. Each pixel of red or green on a Doppler display represents the movement of countless droplets tumbling through the sky. For a trained meteorologist, these images are like the fingerprints of a storm, revealing its hidden structure, its strengths, its weaknesses, and its likely next move. This technology provides the critical minutes of lead time for tornado warnings that save lives, and allows for the precise, targeted flood warnings that let communities evacuate. It is an indispensable tool for aviation, water resource management, and even military logistics. It lets us glimpse the intricate, violent choreography of weather as it unfolds in real time, directly above our heads. With this arsenal of technology, from the humble weather balloon to orbital satellites and ground-based Doppler radar, we have learned to read the language of the sky with a precision that would have seemed like magic just a century ago. Forecasts today are more accurate than at any time in human history. We can anticipate the path of a hurricane days in advance, issue warnings for tornadoes minutes before they touch down, and model the future of the atmosphere with the help of powerful supercomputers. And yet, for all our satellites and simulations, weather remains the master of surprise. The atmosphere is a fundamentally chaotic system, exquisitely sensitive to the smallest, most infinitesimal changes. This is the principle known as the butterfly effect, the idea that the tiny flutter of a butterfly's wings in one hemisphere could, in theory, set off a chain of events that culminates in a major storm in the other. The overall margin of chaos is not a flaw in our science, it is a fundamental truth of nature. Beyond a week or two, the atmosphere's behavior veers into a realm of deep uncertainty. A reminder that we may never achieve perfect prediction or total control. And it is within this margin of chaos that the greatest risks of the 21st century now lie. As the global climate warms, we are loading the dice, pumping more energy into this already chaotic system, making the extreme events we have documented more frequent and more intense. Beneath the blue dome of our sky, weather is in constant, unrelenting motion. Winds turn, clouds form and dissolve, and rains fall. Every gust, every drop, every shimmer of light is part of a living, restless system. To watch the sky is to feel the very pulse of the planet. We have seen on this journey that weather is not just a backdrop to our lives. It is the fundamental rhythm that dictates our food security, our economic stability, and our national security. It is the force that has toppled empires, shaped the course of battles, and continues to carve the surface of our world. To call it Earth's heartbeat is not a metaphor. It is the literal pulse of air and water, the circulation of planetary energy that makes our world and our civilization possible. As we conclude this analysis, the sky outside your window continues its silent, relentless work, carrying the seeds of tomorrow's storms and the calm of tomorrow's dawn. Our ability to understand, adapt to, and cooperate on the challenges it presents will be the defining story of our time. From the tools that observe from within and above the atmosphere, we now expand our view beyond our planet to the ultimate source of energy that drives every weather system. High above the polar regions, shimmering curtains of green, purple, and red dance across the night sky. This is the aurora borealis. And though they look like an earthly weather phenomenon, their origin is cosmic.
Streams of charged particles, known as the solar wind, are constantly ejected from the sun, colliding with our planet's protective magnetic field and being funneled down toward the poles. When these high-energy particles strike atoms of oxygen and nitrogen in the upper atmosphere, they excite them, causing them to glow. What we see as shifting ribbons of light is the atmosphere itself coming alive. This is not just Earth's weather, but space weather, a reminder that our atmosphere is a dynamic shield, constantly interacting with the invisible stream of energy from our star. However, when the sun erupts with a violent solar storm, massive clouds of plasma and magnetic energy stream across space at astonishing speeds. If aimed at Earth, these storms can rattle our magnetic field, sparking brilliant auroras, but also posing a direct threat to our high-tech civilization. A powerful solar storm can disable satellites in orbit, disrupt the Global Positioning System (GPS), and induce powerful currents in terrestrial power lines, with the potential to collapse an entire nation's electrical grid. This is a low-probability, high-impact catastrophe scenario, a space weather black swan that governments and militaries around the world are preparing for. It reveals our fragile dependence on an invisible magnetic shield and the stability of a star 93 million miles away. From the invisible influences of space weather, we return to how our own atmosphere bends and shapes one of the most fundamental forces of all: light. Rainbows appear as graceful arcs across the sky, but in truth, they are full circles of light. We usually see only the top half because the horizon blocks the rest. Pilots, however, sometimes report seeing complete circular rainbows when looking down on storms from above. These optical phenomena are more than just beautiful. They are visible manifestations of the physical laws governing our atmosphere. On very cold days, when ice crystals drift high in the air, strange companions may appear beside the sun. These are sundogs, bright spots of light that sparkle on either side of the sun like phantom stars. They form when sunlight bends through hexagonal ice crystals in cirrus clouds, creating the illusion of three suns in the sky. For ancient peoples, these were omens. For modern science, they are evidence of the composition of the upper atmosphere. Illusions can become even stranger. On hot summer days, desert travelers and highway drivers may glimpse shimmering pools of water on the horizon, only for them to vanish upon approach. This is an inferior mirage, which occurs when layers of hot air near the ground bend light from the sky upward, creating a false reflection of water. Conversely, in polar regions or over cold seas, a superior mirage can occur, bending light downward and making distant objects that are beyond the horizon appear to float in the air. Sailors once told stories of ghostly fleets suspended above the ocean. This is not magic. It is the atmosphere acting as a giant lens, constantly shaping and distorting our reality, a reminder that what we see is not always the truth. The ocean and the atmosphere are not two separate systems. They are one vast, interconnected climate engine. Every few years, a temperature shift in the Pacific Ocean sends weather shock waves across the entire planet. This phenomenon is called El Niño. When it occurs, a vast expanse of warm water in the equatorial Pacific shifts eastward, and the atmosphere responds. Wind patterns shift, ocean currents change, and weather patterns ripple outward across the globe. The consequences are global and disturbingly predictable. South America sees torrential rains and flooding, while parts of Asia and Australia endure devastating drought. The Atlantic hurricane season may be suppressed, while Pacific typhoon activity intensifies. Even winter storms in North America can be altered by the pulse of El Niño. What begins as a change in ocean temperature near the equator cascades into economic and social consequences felt thousands of miles away, costing billions of dollars.
This is one of the clearest demonstrations of how interconnected Earth systems are. For economists, policymakers, and insurance companies, El Niño is not a mystery. It is a predictable factor in global risk models. It affects agricultural commodity prices, energy demand, and supply chain stability. Its counterpart, La Niña, brings the opposite effect, with a cooling of Pacific waters and a reversal of weather patterns. This El Niño Southern Oscillation Cycle is one of the primary heartbeats of the planet's climate, a reminder that the weather on every continent is steered by the silent currents of the vast ocean beneath the sky. Beneath the ocean's surface, currents flow like giant hidden rivers, transporting enormous amounts of heat energy around the globe. These currents, driven by differences in temperature, salinity, and wind, act as the planet's climate regulation system.
Warm water from the equator drifts toward the poles, while colder, denser water sinks and slides back toward the tropics. Without these invisible rivers, much of Earth would be uninhabitable, with sweltering equatorial zones and frozen mid-latitudes. One of the most critical of these currents for Western civilization is the Gulf Stream. Europe lies at a high latitude, on par with Canada, yet its winters are much milder. The reason for this discrepancy flows across the Atlantic Ocean. The Gulf Stream carries an immense volume of warm water from the Gulf of Mexico northeastward, releasing its heat into the air as it travels. This warmer air softens the chill of Europe's winters. Without the Gulf Stream, much of northern Europe would face a climate closer to Siberia's. Entire cities, agricultural economies, and cultures have been shaped by this steady river of warmth. However, scientists are watching it closely, as evidence suggests that melting ice from Greenland is releasing fresh water into the North Atlantic, diluting the cold, salty water and potentially slowing down the pump that drives this circulation. A slowdown or collapse of the Gulf Stream would have catastrophic climate impacts, not just in Europe, but worldwide. It remains one of Earth's most important lifelines, a hidden partner in the dance of weather and climate. When extreme weather and prolonged drought take hold, another threat emerges: wildfire. But when a forest fire burns with intense heat, a terrifying phenomenon can occur. The fire begins to create its own weather system. The intense heat drives powerful updrafts, lifting smoke, ash, and moisture high into the sky. When this column of smoke rises high enough, it condenses into a cloud, known as a pyrocumulus or fire cloud. In the most extreme cases, this cloud can develop into a full-fledged fire-generated thunderstorm, a pyrocumulonimbus. Inside these massive clouds, particles of ash and ice collide and rub against each other, generating static electricity much like in a regular thunderstorm. The result is lightning born from the fire itself. These lightning strikes can hit the ground miles away from the main fire front, igniting new fires and creating a terrifying self-sustaining fire cycle. Firefighters sometimes witness skies flashing with lightning even as flames roar below, an eerie union of fire and storm. This phenomenon shows that weather is not only a force upon landscapes, but also a force created by them. A burning forest becomes a temporary weather system, alive with thunder and fire. As the massive smoke plumes travel into the stratosphere, they can circle the globe, subtly shifting weather patterns thousands of miles away. It is a frightening reminder of nature's power to amplify itself, a reality that is becoming more common in a world that is growing hotter and drier. Human activity has now become a measurable factor in the global weather system. Look up on a clear day, and you may see the long, thin trails left by airplanes. These contrails, formed from hot exhaust mixing with cold, moist air, can linger and spread, merging into thin cirrus clouds. Though they seem delicate, they can alter local weather by affecting how sunlight and heat move through the atmosphere, warming nights and cooling days.
After the September 11th attacks in 2001, when flights were temporarily grounded across the United States, scientists observed unusual swings in day and night temperatures, a hint of how much contrails normally influence the climate balance. On a more direct scale, humans have attempted to manipulate the weather.
The overall mood, called cloud seeding, involves releasing particles like silver iodide into clouds to act as condensation nuclei, encouraging water droplets to form and fall as rain. Though its results are debated, cloud seeding has been used in countries such as China, the United Arab Emirates, in an effort to combat drought or ensure clear weather for major events. This raises complex geopolitical questions. Does one nation have the right to take the rain from clouds that might have otherwise drifted across a border and rained on its neighbor? Air pollution also has a profound effect. Particles of dust, smoke, and aerosols in the atmosphere can make sunsets more brilliant by scattering light, but they also act as cloud nuclei, potentially altering rainfall patterns and even making storms more intense. It is clear that we are no longer passive observers. The footprint of our industrial civilization is now written into the atmosphere itself. Unlike a storm that arrives and departs in a matter of hours, there is a weather disaster that unfolds in silence, over months or even years, with a destructive power that is just as immense. It is drought. When the rains fail, the world changes slowly but profoundly. Crops wither, rivers shrink to a trickle, and the soil cracks under the heat of the sun. Most droughts last for months or years, but in the geological past, some have stretched for centuries. These mega droughts have left scars in tree rings, lake beds, and even the ruins of vanished civilizations. Evidence shows that the western United States endured droughts lasting hundreds of years during the medieval period, far longer than anything seen today. Such droughts reshape entire regions, forcing people to migrate, abandon settlements, and adapt in extraordinary ways. A drought is a silent kind of weather. No storms, no thunder, no spectacle. Just an absence, stretching on and on until landscapes and histories bend beneath it. In the modern world, drought is a catalyst for conflict. It exacerbates cross-border tensions over water resources, causes food insecurity that leads to social unrest, and drives mass migration. In its quiet way, a drought can be every bit as powerful and geopolitically destabilizing as a hurricane or a flood. History is often told as a story of kings and wars, but weather has quietly shaped it from the beginning. Ancient battles were won or lost not on strategy alone, but on the weather. In 1588, the mighty Spanish Armada set sail to invade England, only to be scattered and sunk by fierce storms in the North Atlantic. Centuries earlier, Kublai Khan's fleets were destroyed by typhoons when he tried to invade Japan, storms the Japanese called kamikaze, or divine winds. Napoleon's retreat from Russia was made catastrophic by the brutal Russian winter, while the D-Day landings of World War II succeeded only because meteorologists found a brief window of favorable weather. Weather does not take sides, but it has changed the course of history, deciding the fate of nations. Likewise, civilizations have risen and fallen on the tides of climate. The Akkadian Empire in Mesopotamia and the great cities of the Indus Valley both collapsed after sudden climate shifts led to prolonged drought. More recently, the ancient Mayan civilization, with its towering cities and advanced astronomical knowledge, collapsed. Strong evidence points to a multi-decade drought that caused crop failure, increased conflict, and led to the abandonment of their great cities. When we look at ruined temples and empty cities, we often see the fingerprints of climate. Human history is inseparable from the story of the sky. It is a humbling reminder that even the greatest cities depend on the rains to come. In the chaos of battle, the sky above is sometimes the most powerful commander of all.